Hi everyone! In this video I want to work on evaluating a little bit messier looking log statements. In particular I want to look at some that have variables involved and figure out if we need to have any restrictions on what the values of those variables can be. So the first couple are similar to things we worked on in our first evaluating logs example, but there's a variable in the mix. So when I look at this, log base 3 of 3 to the x, I should automatically be asking myself what power of 3 will give me 3 to the x? And the answer should be x. If I raise 3 to the x power, I get 3 to the x power. You can see my question over here, so I don't forget to ask you. When there's a variable involved, it's really important to think about, is this true for all x values, or is this only true for certain x values? So this again is pushing you to continue thinking about this from a functions perspective and not just from an algebra basic operations perspective. I would look at this as I've composed inverses. We did this in a previous example. When you take the log base b of b to the x, you get x. And that's great, but that should only have to be true if we're within the domain of the inner function. So the way this one works out is your x value first goes to the exponential function, which can take all real numbers. You can raise 3 to any power you want. Whatever you get out of the exponential function should automatically work for the log because they are inverses. That shouldn't be a problem. So you should not get in trouble on the second step here. It's just that very first step of raising 3 to the power. So the answer is no, there are no restrictions. That's true for absolutely all real numbers x. Okay, kind of similar. This is saying what power of 10 will give me 10 to the 2 minus x. So don't forget, if you don't see a base on a log, it's an implied 10. So if you ever see plain old log, always assume you're looking for powers of 10. And once again, we're seeing kind of an inverse thing happen here. The log base 10 and the 10 to a power are inverses. We don't have anything to get rid of the 2 minus, so that's going to stick around. We don't just get plain old x because they're not perfectly inverses, but raising 10 to a power and taking a log base 10 are inverse operations, so we at least get to go as far as canceling those. Once again, if there's a variable in the mix, we should be able to say whether or not there are restrictions on when that's true. And just like before, there are no restrictions on this one. The x first goes into the exponent. You can raise 10 to absolutely any power you get here. So since it first is the exponential function and then the log function, we're not going to have any trouble. So no matter what x we start with, if we raise 10 to the 2 minus x and then take the log base 10 of that, we're just going to get 2 minus x. Okay. We want to switch it up a little bit here and try the other direction. This looks a little trickier, but should work out very nicely as well. So the first few, I deliberately gave you some that work out really nicely just to make sure that you're convinced about how this does work. This is raising an exponential function to a log power. So the order here is take the 8, plug it into the log, take whatever you get, and apply it as a power of 2. The log base 2 of 8, I can actually figure that out. So just this part, ignoring the 2 out in front, this is asking me what power of 2 gives me 8. And the answer, hopefully you can hear me, I'm just realizing my headphones are far away. The answer is 3. So the log base 2 of 8 is equal to 3. If I then take the 2 and apply that third power, I get back my 8. So pay really careful attention to how that worked. I took the log base 2 of 8, meaning I asked myself what power of 2 would give me 8. I then apply that power to a 2, and I get an 8. So that should make sense. It's a little bit round and round, but I hope that makes sense that that's how that works out. This is another one that we can walk through step by step. So the first step is take the natural log of 1 over e. So that's asking what power of e will give 1 over e. And the answer is if I want to flip the e over, I need a negative first power. So the log is equal to -1 because the negative first power of e is 1 over e. If I then apply that negative first power to this e, I will, of course, get 1 over e. I know those are a little weird, but try and think through them carefully because if you think through them step by step, you should see that it makes sense to be getting back what we started with. Okay, I got one more like this, and then we'll try some messier ones to make sure you're seeing the pattern. Okay, so here, first I take the log of 100, then I raise 10 to that power. To take the log of 100, I should ask myself what power of 10 gives me 100? And the answer is a second power. So the log of 100 is 2. I'm then supposed to apply that second power to the 10, which is going to give me 100. So once again, I say what power of 10 gives me 100? And then I apply that power to a 10, and I certainly better get 100. All right, so if this is making sense, I've got some that are a little messier. If I ask you for pi to the log base pi of 17, I'm saying first find the power that you would apply to pi in order to get 17. That's not an easy thing to say. I don't know exactly what power. I know pi is close to 3. 3 squared is 9, so it's probably a little bigger than 3, but it's not some nice integer power. However, if I pay attention to what happens next, I first find the power of pi that would give 17, and then I apply that power to pi, so I better get 17. If you apply the power of pi to get 17 to a pi, you should get 17. Okay, down into the variables, and then I'm going to write something off to the side, and hopefully it'll be clear to everyone what we're getting at here. Here I have a variable, so I'm really not going to be able to give a number answer. I'm asking what power of 1/2 will give me x, and then whatever that power is, I'm applying it to a 1/2, so I better get an x. I'll talk about restrictions in just a minute. I want to snag this group right here, and I want to generalize. What I hope you've seen now, and again, this isn't like a memorization fact, this is an understanding logs fact. So if you're understanding logs, I'm hoping that you can see, this is a little trickier than the other way, that if you take b to the log base b of x, you're always going to get x. Mostly always. We'll talk about the mostly in a minute. Again, this one's a little trickier, but if you're asking yourself what power of b gives you x, and then you apply that power to b, you should get x. So that's on the operation level. On the function level, once again, this is composition of inverses. So up here we looked at log base b of b to the x. That's plugging an exponential function into a log. Here we're looking at b to the log base b of x. That's plugging a log function into an exponential. And they are inverse operations, so you should just get back what you started with. The other part of this is, are there any restrictions on this one? So if we plug the log function into the exponential, is this true for all x values, or does it only work for certain x values? And the answer here is it only works for certain x values. The step-by-step here is first plug it into the log, then plug it into the exponential. Anything you get from the log will work for the exponential. There's no trouble with that step. But you could get in trouble trying to plug x into the log, so this should always be a positive x. The thing you plug into a log has to be positive. And the exact same will hold down here. This will only work if x is greater than 0. Okay, so similarly, if we take 5 to the log base 5 of 2x plus 1, we're asking what power of 5 will give us 2x plus 1, and then we're applying that power to 5. So we'd better get a 2x plus 1. This should not be true for all values of x because you can get in trouble taking the log of 2x plus 1. We need to make sure that 2x plus 1 is greater than 0. So not just x greater than 0, 2x plus 1 has to be greater than or 0. The whole thing you're taking the log of, which means 2x has to be greater than negative 1. So x has to be greater than negative 1/2. So that will be true as long as we choose an x value that makes the thing inside of the log positive. All right, very last one here. If I take the natural log of an e to the 3x, I should be asking myself what power of e will give me e to the 3 minus x? And the answer is a 3 minus x. So again, we're seeing their order of operations. If I plug an x in, I would first subtract it from 3. I would then exponentiate base e. I would then take a log base e. Since the exponentiate and the log are inverse operations and they happen one right after the other, they should wipe each other out. So we get this 3 minus x. And once again, if there's a variable involved, you should be able to tell me if there are any restrictions on what the value of x can be. And here there are not. People are really tempted to say x has to be, I don't know, which way would it be, less than 3? Yeah, I think less than 3. But this time the exponential function is actually the inner function. So x can be anything. I can raise exponentials to any power. So the answer here on the restrictions part is no, there aren't any restrictions. That's true for all real numbers. All right, thanks for watching.